Hello viewers, welcome to this lesson. Our topic is vectors. This is a topic that we are going to do it in two sections. The first part is vectors in 2D coordinates and the second part is vectors in 3D coordinates. Now, the 2D coordinates vector, we are going to do it in this lesson, and then the 3D vectors in 3D coordinates, we'll be doing it later in the next lesson. So keep in touch with the channel. Now let's get started. We are going to define the two terms, vectors and scalars, and therefore we say that a vector is a quantity with both magnitude, that is length, and direction. So the other name of magnitude is length, distance, or even modulus. Now, examples of vectors is gravity, we have velocity, and force. On the other hand, we have a scalar, which is a quantity that has magnitude only. And examples are time, speed, and mass. Now, a vector is named using the letters at the end of the directed line segment or using lowercase bold or underlined letters. So this is what we are talking about. We have a point A. We have a line AB. The line is shown using the direction, and therefore that now makes it to be a vector. And now the vector is named as AB with the arrow. So that is vector AB, or vector U, and U is bold because we have said a vector can be named using lowercase bold letter. Another one, the vector can also be written as vector U with underlined letter, that is letter U. So those are the three ways in which vectors can be written. Now let's look at vectors in 2D coordinates. This is the two-dimensional coordinates of a vector. Now we are starting with the magnitude of a vector, and then we say a vector's magnitude is represented by PQ. Of course, this is an example. PQ is vector PQ. We have vector PQ, and then the magnitude of this vector PQ will be, you have to put these bars, side bars, to show that it is the magnitude. Otherwise, without the side bars, it will still be vector PQ with the arrow. But now when you introduce the side bars, then it will be the magnitude of a vector. Now, on the other part, PQ can be, we have the magnitude of vector PQ, or the magnitude of vector U, because we are getting this from our previous diagram. We are getting this from our previous diagram. And now, a vector's magnitude is calculated using Pythagoras theorem, and this can be illustrated below. We have vector PQ, which is given as vector U with the underlined letter U. And so we are supposed to find the magnitude of vector PQ. That can also be said to be magnitude of vector U because they mean the same thing. So the Pythagoras theorem here will be, we have the square root of a squared plus b squared. Of course, a and b are the coordinates. And so we can look at this example, calculate the magnitude of the vector. So we have vector CD, which is the same as vector W. So the coordinates of vector CD is 4, 2. Now we are supposed to calculate the magnitude of this vector. Even how we are going to write this the magnitude is going to change. Now we have the magnitude of vector W is equal to square root of A squared plus B squared, because we have A, the value of A, and the value of B, because they represent the coordinates given in the vector. So we have magnitude of vector W will be square root of 4 squared plus 2 squared. That will be root of 20. And this is a third, which we can also simplify it. So that will be magnitude of vector W equal to root 4 times root 5. And root 4 is equal to 2. So we have the magnitude of vector W to be 2 root 5. Just as simple as that. Now number 2, calculate the magnitude of the vector. And the vector here is PQ with now different coordinates. That is -4 and 3. Now we are going to say that the magnitude of vector W equal to the square root of A squared plus B squared. Then we substitute, because we have the coordinates, the real values of the letters there. So we have the root of -4, and remember -4 should be in bracket because we are squaring, plus 3 squared. So this will give you root 25 if I'm not wrong, and root 25 is 5. So the magnitude or the length or the distance or even the modulus of vector W is 5. Now let's move to equal vectors. Now we say that vectors are equal only if they both have the same magnitude and direction. So those are the conditions for vectors to be equal. And therefore, vectors are also equal if they have equal components. And for vectors, we have the following vectors: U with coordinates A and B, and vector V with coordinates C and D. Now if vector U is equal to vector V, then we have that A is equal to C. For them to be equal, we are talking about the equal components. Now, because the two vectors are equal, then that means their components should also be equal. So A is equal to C and B is equal to D. Now, by working out the components of each of the vectors, determine which vectors are equal. So here we have vectors from A up to G up to H. Now we are supposed to determine which of the vectors, which set of the vectors are equal. If you look at vector A, and remember, before we come up with the equal vectors, we need to be reminded that equal vectors, the conditions for which vectors are equal. So vectors are only equal if and only if they are of the same magnitude and direction. So if you look at A and B, they are not equal because they are not in the same direction. A and C, they are not in the same, they are not equal first. In the first place, the magnitude is not equal, their magnitudes. and they may be, they are of the same direction. If you look at A and D, not the same direction. So the vectors, a set of vectors that are equal in this case is A and G. A and G is the only set of vectors that are equal. Now, let's move to addition of vectors, and any two vectors can be added in this way. So we have been given vector A and vector B. We are supposed to add it and be able to find the resultant sum of the vectors. And now, this is what we do. So you realize that the other one was joined with vector B is joined to vector A, and now if you add them, you'll get vector A plus vector B. So suppose vector A is given the coordinates 2, 4, and vector B is given the coordinate 6, -3, then the resultant vector will be, that is vector A plus vector B, and that will be, you take A, which was 2, 4, plus B, which is 6, -3, then the resultant vector will be 8, 1. And the most important thing here is the arrows must be nose to tail. You realize that you noticed when we were joining B to vector B to vector A, then it was nose to tail. That is the concept that we are going to use here. The nose of B to the tail of A. That is the concept. Now, another part on addition. So we have this diagram here. It is in the form of a triangle ABC, and then we are asked that let vector AB be 3, 4, and vector BC be 2, -5. Therefore, we can find vector AC. Vector AC will be equal to AB, that is vector AB, plus vector BC. So we can substitute because we have vector AB and vector BC. So we'll have 3, 4 plus 2, -5 is equal to 5, -1. And vector AC is equal to 5, -1. That is the coordinate for vector AC. Now, in general, we have that for vectors U and V, if vector U is A and B, and vector V is C and D, then if we add the vectors, that is vector U plus vector V, then we shall get vector A, B, that is U, plus C, D, that is representing V, that is vector V, is equal, we are adding the components. So we will get A plus C, and then B plus D. B plus D. B for boy plus D. Okay. Let's move to zero vector. And we have that, you can see vector AB and vector AB, and be very keen because the arrows are not the same. They are not showing they are not in the same direction. One is, for the first part, is pointing towards B, and the second part is the reverse of the first part. And now, if vector AB is equal to 1, 2, then vector BA, so you realize that we have reversed the movement. So it's going to be negative. So vector BA will be -1 and -2. So therefore, we can sum up. So we have AB, vector AB plus vector BA. We have 1, 2 plus -1, -2. That will give us 0, 0. And that is what proves what is called the zero vector. Now, 0, 0 is called the zero vector, written zero vector. That underlined part shows the vector part. Now, negative vector is another part that we want to talk about, and we have this diagram, vector AB and vector BA. So also they seem to be the same, only that they are not in the same direction. So vector BA is the negative of vector AB, just the reverse of AB. So we have that for any vector u, so we have vector u plus vector -u. So vector u represent vector AB, and vector -u represent vector BA. So we'll get vector u plus negative vector u, and that will give you 0. Now, if vector u is given as AB, then it means vector -u, which is the reverse, will be given as -a and -b. Now, moving to subtraction of vectors, we have that any two vectors can be subtracted in this way. So we have two vectors here. We have vector u and we have vector v. So we are going to perform this, and then given that, or rather suppose vector u is equal to 6, 3, vector v equal to 1, 3, then that means that vector u minus vector v will get 5, 0. But now we want to see how. We are taking the equivalent for vector u, that is 6, 3, minus the other coordinate for v, vector v, 1, 3. So you'll get 6 minus 1. We are subtracting the corresponding components. So 6 minus 1 will get a 5. Then 3 minus 3, 0. So also we are keen to notice arrows moving nose to nose. Arrows are moving nose to nose. We are very keen there. And then on the other part of subtraction of vectors, we have this diagram. We have vector A and vector B, which were joined together to get vector. I think here the subtraction took place. So we have vector A minus vector B. Of course, the arrows are moving nose to nose. And so we let vector A to be 6, 5 and vector B to be 2, 4. So we have that vector A minus vector B can also be written as vector A plus minus vector B, and that will be, we substitute, so we have 6, 5 plus minus 2 minus 4, and the answer is 4, 1. So that is the resultant difference of the vectors. So we have 4, 1 is the answer. This is an alternative. You can also perform it this other way. You can also do it this other way, whereby you take 6, 5 minus 2, 4 is equal to 4, 1 directly. Still you get the same answer. Now in general, we have that for vectors u and vector v, then if vector u is equal to AB and vector v equal to CD, then vector u minus vector v will be given as AB minus CD. So in this case, we are going to subtract the components. So that is A minus C and B minus D. The next part is multiplication by scalar. So multiplication by a scalar. Scalar can be a number or represents a number or even a letter. So if we have vector v given as x and y, then kv will be, we are now multiplying vector v by a scalar, and our scalar here is k, and k seems to be a constant. So we have, if we open the bracket, it will be k multiplying xy, so it will be kx and then ky. Then the vector kv is parallel to vector v of different size. They are of different size. Hence, if vector u is equal to kv, then this means that u is parallel to v. Vector u is parallel to vector v. So of the same reason that we have just talked about. Now, conversely, if vector u is parallel to vector v, then it also means that vector u is equal to k vector v, that is kv. Okay, on the other part of multiplication by a scalar, so we need to show that the two vectors are parallel. So the two vectors are vector w given as 6, 9, and vector z given as 18, 27. So we are going to show that the two vectors are parallel by using a scalar, the concept of a scalar. So if the vector z is equal to kw, that is k vector w, so it means we multiply one side of the vector by a scalar and equate to the other remaining vector. So vector z is equal to kw, that is vector w. Then we have that vector z is parallel to vector w. So this can be illustrated. So we have vector z is equal to 18, 27, and we are equating to kw, and we can get the value of k, because if you multiply kw, then you'll get 6k, then equate the components. So it will be 6k is equal to 18. So the value of k there will be 3. So definitely it is 3 into 6, 9. So that means that vector z equal to 3 vector w. So we have also an alternative method, another approach, whereby now we are going to equate vector w to be k vector z, so that we see if we can still get the same answer. So in this case, we have, if vector w is equal to k vector z, then vector w is parallel to vector z. So we have vector w is equal to 6, 9, and on the other side, if you work on the k, then you'll get 1 over 3. So it will be 1 over 3 of 18 and 27. So that means that vector w is equal to 1 over 3 vector z. Okay, on the other part is unit vectors. So we are going to talk about the unit vectors, and we have that for any vector v, there exists a parallel vector u of magnitude 1 unit. That's why we call it unit vectors. This is a vector of magnitude 1. And so the vector is called a unit vector. So we have that, let's look at this as an example. Find the components of the unit vector u parallel to vector v if vector v is given as 3, 4. So we are going to find the magnitude of v, of vector v, and because this is two-dimensional coordinates, we use the Pythagoras theorem, the square root of a squared plus b squared. So to find the magnitude of vector v, it will be the square root of 3 squared plus 4 squared. So that is the magnitude of vector v is equal to 5, because we have 9 plus 16. So we'll get root 25, which we can get the exact root. So the unit vector is u, and therefore we can now get, we have that the vector u is equal to 1 over 5 of v. So we have vector u is written as, because they are parallel, so that means it will be vector u is equal to k vector v. So we find the value of k, which is a scalar. Now the scalar is 1 over 5, and so it will be vector u is equal to 1 over 5 of 3 and 4. So that means 3 over 5 and 4 over 5. On the next part of this topic, we have position vectors. So on the diagram, you can see we have from the origin to a certain point we have A. Then again from the origin to a certain point, to a certain part, we have B. So A is the point 3, 4, that is the coordinates, and B is the point 5, 2, the coordinates. So we have to write down the components of vector OA and vector OB, and finally vector AB. So if you look at this very well, you will find that vector OA is the same as vector A minus, is the same as A minus O, whereby O is the origin, that is 0, 0. It is of coordinates 0, 0. So you take the coordinates for point A, is 3, 4 minus that of the origin 0, 0. So you still get vector OA to be 3, 4. The other one for vector OB will be 5, 2. And AB will be, AB is the same as OB minus OA, minus OA. So OB is 5, 2. So minus OA is 3, 4. So you subtract, you get 2, negative 2. So this is what we are talking about is vector AB, which is vector OB minus vector OA. So you'll get 5, 2 minus 3, 4. And the answer will be 2, negative 2. So that is the answer for the vector AB. Now, still on position vectors, so we have vector OA is represented by the small vector A, and vector OB, which is the position vector of B, represented by the vector A, by the vector B, and the position vector OA is represented by the vector A. Now, vector OA is called the position vector of the point A relative to the origin O, and written as vector A, small a. On the other side, we have vector OB is called the position vector of the point B relative to the origin, and written as small vector b. So that means that vector AB is equal to vector AO plus vector OB. So remember, vector AO is negative, so it will be negative A plus negative vector A plus vector B. So that gives us, you now rearrange the signs where the addition is given priority. So it will be vector B minus vector A. That is the vector for solution for vector AB, solution for vector AB in terms of vector small a and small b. Now we have that vector AB is equal to vector small b minus vector small a, where vector small a and vector b are the position vectors of A and B. Now we have a question here. If P and Q have coordinates 4, 8 and 2, 3 respectively, then find the components of PQ. So if we have PQ, then that means that it's going to be Q, the position vector of Q, that is OQ, minus OP. So in simple terms, it is Q minus P. Okay, so we have vector PQ to be Q minus P, vector Q minus vector P. And so we have, because we have the coordinates for P and Q. So the one for vector Q is 2, 3, minus the one for P is 4, 8. So the answer is negative 2 and negative 5. So graphically, we can also perform position vectors, and we have point P of coordinate 4, 8, also point Q of coordinate 2, 3. So we want to find vector PQ, whereby we have vector OP, that is the position vector of P relative to the origin is small vector p, and the position vector of Q relative to the origin, that is, it's going to be Q, small vector Q. And so PQ, so we need to find the value for vector PQ. So it will be Q minus P, and that means you can do your you can substitute, because now we have what is for Q and what represents P. So the answer will be -2 and -5. I think we did this before. Now our next part of the lesson, as we near to close, is collinearity. And we have a reminder from chapter 1 that points are said to be collinear if and only if they lie on the same straight line. That is for points. Again, for vectors are said to be parallel, because the concept of parallel vectors will be used in collinearity. So for parallel vectors, then for vectors to be collinear, for points to be collinear, there must be two conditions. Their vectors must be parallel, and there should exist a common point. So for vectors, we have, so of course the points that you are given, you change them to vectors. If you are given point A and point B, then probably we have a vector AB. So if vector AB is equal to K vector BC, so this means that the points were A, B, C. So that we get the vectors AB, we get another vector BC, and another vector AC. But for collinearity, we are going to pick only two sets of vectors. That is AB, or rather 2 points. That is AB, vector AB, and vector BC. So we want to show, or rather prove, that these two vectors are parallel, and then we identify a common point. That is when collinearity will be achieved. So if AB vector is equal to KBC, where K is a scalar, then we have that AB is parallel to BC. So if B is also a point common to AB and BC, then we have that point A, B, and C are collinear. So that is exactly what collinearity is all about. So there must be two things. Their vectors, for collinearity, their vectors are parallel, or must be parallel, and there should exist a common point. In this case, our common point is B. Now, let's look at this question in this part. Prove that the points A 2, 4, B 8, 6, and C 11, 7 are collinear. So we need to work out on the parallel part of the vectors. So because we have the points, it means we can get the vectors. So we have vector AB, which is given as b minus a, that is vector small b minus vector small a. And we are going to substitute to get the value of vector AB. So we have 8, 6 minus 2, 4, and this is equated to, we will get 6, 2. The other part of the vectors, we have vector BC, which is C minus B, and that is substituting on the coordinates. We have 11, 7 minus 8, 6, and that we get 3, 1. Now, I said you only take two vectors. You only consider 2 vectors. We can't really go for the other part, which is AC, because we will not really manage with the parallel. For parallel vectors, we can only consider 2 vectors. So that means vector AB is equal to 6, 2 is equal to 2 into 3, 1. So 2, you realize it is a scalar, that is the k, the value of k, and then 3, 1 is for BC. So that means vector AB is equal to 2 vector BC. Vector AB is equal to 2 BC, whereby it's the same when we say that vector AB is equal to k vector BC. So that means the value of k is given as 2, rather you have to find it, and in our case it will be 2. And so since vector AB is equal to 2 vector BC, then AB is parallel to BC. Okay, parallel to BC. So that means B is a common point to both AB and BC. And so the points A, B, and C are collinear. So that is enough proof for collinearity from the question given. And now let's now introduce the other concept, the ratio theorem. Introducing the ratio theorem. Ratio theorem, basically it involves the division of a line either internally or externally. So it is a summarized formula that will be used to divide a line internally or externally, and we are going to use it especially when the ratios are given. Okay, so we have point O, we have this, there is a triangle here which is not completely drawn. We have OAB, and on the center line, not really the center, but some part close to A, part on the line close to A is subdivided, or is divided by S. So S divides AB in the ratio that we still don't know. So that is basically this, like I said, it is a triangle whereby its parts are not completely drawn. So we have AS is 1 and we have SB is 2. So meaning AB is of length 3, and Now we have vector OS is equal to vector OA plus vector AS plus vector AS. So that means that we have the total length being 3. Total length is 3. And so we can now say that vector OS can be given as OA. So you are starting from O moving to S. So that means you need to move sequentially. So it will move from O to A and then from A to S. That is exactly what we have said in the first part. So the second part, we are just trying to fix the values if we have them. So we have vector OA plus AS. AS, of course, it will be a third of the whole length, or rather the whole line, which is AB. So vector AS is a third of vector AB, because we have vector OA given as small vector a and vector OB given as small vector b. So we can substitute it there, having that we can also recall that vector AB is given as vector b minus vector a. We just did that in our previous part, And so we have vector s, that is small s, is given as, is equal to small vector a plus a third into b minus a, that is vectors. So we are going to open the bracket to simplify further. So if you do that, of course, we have vector a plus a third vector b and minus a third vector a. So we shall have, if you simplify, 2 over 3 vector a plus 1 over 3 vector b. So that is the value of vector s. Now we want to derive the ratio theorem so that it can be easily used in a question. Okay, now we have the same diagram. We have OAB, which is an incomplete triangle from O to A to B. So that means we have the length AB, and the length AB has been divided by letter P. So we have AP given as M, and we have PB given as N. So that means vector OP is given as vector OA plus vector AP plus vector AP. So we have, that is correct. Okay, the whole length from A to B is given as M plus N, the whole length, because we have the section, the ratio M, and another one, the ratio N. So the whole length is M plus N. Now, OP, vector OP is equal to vector OA plus M over M plus N vector AB, vector AB. Now, we have that. We are just doing what we did in the previous example, because AP is going to be the fraction of the total length. So we have m of the total length, which is m plus n. So the fraction there will be m plus n m over m plus n of the vector AB. So that is exactly what is in the second part. Now we need to move to the third part. So before that, we need to know that OP, that is the position vector, and it is represented by small vector P, OA, small vector A, and OB, small vector B. Now, we have OP being small vector P equal to vector A, that is small vector A, plus the fraction m over m plus n into bracket AB. Vector AB is the same as B minus A. So that is what we have. If you can open the bracket and simplify, then you will get vector P is given as n over m plus n of vector A plus m over m plus n of vector B. So this is the ratio theorem, and in the next question, or in our next question, we are going to use the ratio theorem to be able to solve for the point which is going to bisect on the main line. So we can summarize the ratio theorem by a question. So we have a line AB. We have a line AB, and P is a point on the line AB. It divides the line AB at a certain point. So we have AP to be M, and we have PB to be N. And now we say that if P is a position vector of the point P, then that divides AB in the ratio M to N, then we have that vector P is equal to N over M plus N of vector A plus M over M plus N of vector B. So that is, we're coming back to the ratio theorem. So that means P has divided AB internally, and probably in our next lesson we shall be talking about the division of a line externally, the external division of a line using the ratio theorem. So keep in touch with the channel. So let's now summarize this concept of ratio theorem with a question. So we have A and B have coordinates -1 and 5 and 4, 10 respectively. So we have A is for the -1, 5 and B for 10. So find P if AP ratio PB is 3:2. Find P if AP ratio PB is 3:2. That is the question. So we have a line AB which is internally divided by point P, 3, to 2, that is the ratio. So to find P, we just use the ratio theorem. You substitute in the ratio theorem, whereby we said n over m plus n of A plus m over m plus n of vector B. So 3 is m, represent m, and 2 represent n. So that means, of course, we have A. What is the value of A? So we have 2 over 5 of vector A, which is negative 1, 5, plus 3 over 5 of vector B, that is 4, 10. So we get negative 2 over 5, 2, plus 12 over 5, 6. Then we sum up to get 10 over 5 and 8. So that means vector P is 2, 8 in column vector. That is 2, 8 is in column vector. But if you are asked to find the coordinate of P, then it's going to be 2 pair or comma 8. 2, 8 or 2 pair 8.